Good morning to all. Welcome to this 10th online lecture session of the course Engineering Thermodynamics. In our previous lecture, we had a discussion on the steam tables, and we have practiced that how to employ steam tables for finding the thermodynamic properties of the system when our system is particularly involving water as our substance. Okay. Now, related to steam table only, let me just further explain the concept of equation of state. Okay, so that we know that if we have any equation which relates our primary fundamental properties, primary measurable quantities such as pressure, specific volume and temperature. So any equation which gives the relationship between these three fundamental measurable properties, we call that equation as nothing but equation of state. Okay. Now, based on certain assumptions, we have one specific type of equation of state. That particular equation is known as ideal gas equation. Okay. So, we have one equation of state which is particularly known as ideal gas equation of state. So, as per ideal gas equation, we have PV equal to RT, where V is specific volume, P is pressure, R is gas constant, which is specific to a particular type of gas, and T is nothing but our temperature, and we take this temperature in Kelvin, absolute scale. Okay. So, this is our ideal gas equation, and this type of equation is based on certain assumptions, and the two very important assumptions are that our molecular volume is negligible in comparison to the volume of our container or volume of our system, and apart from that we are not having any molecular interactions. Okay, so we say that the molecules are far apart from each other, so they are not having any molecular interactions. Okay, so these particular assumptions are applicable for majority of the gases at very high pressure. Okay, so when we have high pressure and low temperature, under these assumptions of high pressure and low temperature, this equation actually holds good. Okay, now what we have to do over here, so particularly if we see our steam table. Okay, so particularly if we go to our steam tables, or I should say the property diagrams. If I go to property diagrams, in case of superheated region, for water, in case of superheated region, we know that in superheated region our water is existing in the vapor state and it behaves like a gas. So if we are having superheated state where our substance is behaving like gas, then under the conditions of, so previously I have written the condition of ideal gas as wrong, so it should be low pressure and high temperature. Okay, so I have mistakenly written it wrong. So under the assumption of low pressure and high temperature, our gas behaves as ideal gas. Now if I go to the steam tables, in case of superheated state, there we know that already our substance behaves like gas, and the superheated portion of our steam table where we are having low pressure and high temperature, this particular region can be explained with the help of a ideal gas equation. Okay, so we know that in case of ideal gas equation, the dependence will be on single property. So that is something which will be applicable in our steam tables also if we particularly go to this region. Okay, and we will be having actually nothing but the direct relationship in between the properties of steam which we were having in case of ideal gas equation. Okay, so now that let us try to see. So now if I plot a temperature volume diagram. Okay, so if I plot temperature specific volume diagram, this is my liquid vapor dome, and let me consider that this is my high pressure line and this is some low pressure line having pressure P1. So this is having pressure P1 and another one is having pressure P2 which is greater than P1. Okay. Now if I extend this particular line, if I extend this particular line P2, and similarly if I extend this line of P1 also, so whatever the slope I was having in whatever the slope I was having in P1 region, that slope only I am extending over here. Okay, so it may appear to you diagram wise that slope of this dashed line and slope of this firm line over here is different. So that is just because I want to make these lines to cross at origin. Okay, but what you have to remember that in actual practice what we are having, so this diagram wise it is looking different in dashed portion and in firm portion whatever I am having over here, but in actual practice this slope and this slope they are actually same. So what we are doing, whatever the slope of this line we are having in superheated region, slope of constant pressure line, I am extending a line of same slope, and finally we will be finding a situation that these lines will be crossing at absolute temperature. Okay, so corresponding to the absolute zero condition, these lines will be crossing. So it means you can clearly say that if I have these two lines, so the equation of this line will be nothing but equal to T is equal to A times V. Okay, because this is a straight line and this straight line is meeting at 0. So that's why intercept will be equal to 0. So I am saying that equation of my this straight line is nothing but T equal to A into specific volume. Okay. Now if you see the slope of this particular first line, so if I call this as slope 1 and if I call this another one as slope 2, so you can clearly see that the slope of second line is high in comparison to that of the slope of the first line. Okay. So if slope of second line is more in comparison to slope of first line, it means we can say that this A over here is nothing but the constant representative of slope, because we know that our equation of straight line is nothing but equal to y is equal to mx plus c. Okay, so it means if you now relate, so y is your temperature variable, x is your specific volume, and slope is nothing but a, and intercept is 0 over here. Okay, so now what will be happening? If you see, when our pressure is increasing, upon the increase of the pressure, value of slope is also increasing. So it means that our slope A is directly proportional to pressure. If A is directly proportional to pressure, it means in that case what will be happening? I can say A as nothing but equal to A naught times P, where A naught is some constant. Okay. So now what will be happening? What will be happening if I substitute this expression of A into my main equation? I will be finding that T is nothing but equal to, instead of A, I can write A naught into PV. And finally, I will be getting that PV is nothing but equal to 1 by A naught into T. Okay. Now, if I see the ideal gas equation, we already know from ideal gas equation that PV is equal to RT. Okay. So, it means that in case of our steam also, we are having certain region on the superheated temperature table, a superheated zone, where we are having actually the behavior of the substance, the behavior of water in vapor phase identical to that of ideal gas. And if we try to represent the equation of state for this substance, it takes the form PV equal to 1 by A naught into T, where this A naught is nothing but some constant, and we know that in our ideal gas equation PV equal to RT, where R is also a constant. So it means ultimately what is happening, ultimately we are finding some relationship in between pressure, volume and temperature, and that relationship is actually becoming identical to that of the ideal gas equation. Okay, so it means our water also in superheated zone behaves like ideal gas under certain conditions of low pressure and high temperature. Okay, so that now let me once again explain the same concept with the help of PT diagram also. So it is not the case that when I am drawing the PV diagram then only this thing will be happening. Instead, if I draw say PT diagram, there also this same condition will be applicable. Okay, so let me just explain. So let me consider in this PT diagram, this is my vaporization line. So if this is my vaporization line, so what will be happening? The region on the right of vaporization line will be vapor and on the left will be liquid. Now, if on this particular curve, if I draw the constant specific volume lines, okay. So what I am doing now, I am drawing constant specific volume line. So this particular line is having specific volume say V1, and this another line is having say specific volume V2, and obviously if you try to see the magnitude of this specific volume, V2 will be less in comparison to V1. Why? Because corresponding to each temperature value, the pressure corresponding to V2 line is more. Okay, so if pressure is more, so obviously our fluid will be more dense and it will be having less specific volume. Okay, now if you want to see the equation for this particular type of behavior, you can see that our pressure will be nothing but say B is my slope of the line, B times T. Okay, and now if you see what is happening, basically while your value of B is increasing, corresponding to that specific volume is actually decreasing. So it means our B is nothing but inversely proportional to specific volume. If B is inversely proportional to specific volume, I can write B as nothing but B naught Y small v. Okay, and this ultimately what will be happening if I substitute in the main equation, P will be equal to B naught Y V into T, and finally I will be getting PV is equal to B naught into T. So this is also once again identical to our ideal gas equation. Okay, so it means that irrespective of the property diagram, this is generic nature of the substance, that if we go to superheated region, we are having the ideal gas relationship which is applicable, or I can say the equation of state identical to that of ideal gas equation is actually applicable for our water also, particularly in superheated region. Okay, so now this, but one already I have told you that whatever this assumption we are having, that will be only applicable for a limited condition. So limited condition is that it will be applicable for low pressure and high temperature. Okay, so now let us try to see
Sir,
detailed
sir,
uh,
how is V2 less than V1?
because if every temperature you try to see, so for example if I take any value of temperature, say this temperature, okay, so at this temperature, if for the first line you see value of pressure, it is say P1. At the same value of temperature, if you see the value of pressure corresponding to second line, that is nothing but P2, and our substance in this region is nothing but in the gaseous phase. So it means that my P2 is greater than P1 at same temperature. So if at same T, P2 is greater than P1, obviously my density ρ2 will be greater in comparison to ρ1. Okay, so basically I am calling this point as say 1 and this point as say 2. So my ρ2 will be greater than ρ1 at same temperature. Okay, and if ρ2 is greater than ρ1, so it means our specific volume V2 will be less than specific volume V1 because it is reciprocal of density. Okay, so that will be happening at same temperature. So that's why I can write that my V2 is less than V1. Okay, now
Sir, in ideal gas equation, we use
PV is equals
specific
to so
we
PV
use
is equals to
specific
RT.
volume.
it is
So
better
A
if
should
I
be molar volume.
it is better if I take all your questions later in the doubt clearing session. Okay. So that will be better, I think. So let us now try to complete our content. Otherwise, it will be more of a doubt clearing session rather than a lecture. Okay. So what the main idea is that we are having PV is equal to B naught into T. So it means that under certain conditions we are having our steam also behavior identical to that of an ideal gas. Okay. So what are the conditions under which this behaves as ideal gas, that let us try to see from this particular slide. Okay. So in this particular slide what I have nothing but temperature along ordinate. So this is temperature, and along abscissa I have specific volume. Okay. And on this temperature volume diagram you can see I have this different pressure lines. So you can see first pressure line is say 0.8 kilopascal, 10 kilopascals. So like that I am going till the very high pressure of 20 or 30 megapascals also. Okay. Now if I over here what if I do, if I now on these different pressure lines, if I take multiple points and corresponding to each point if I try to plot the error, so how I will be taking the error, what I am doing basically, I am first taking volume from steam table at any value of given temperature and pressure, minus I am doing volume which is obtained using ideal gas equation or whatever the equation just now we have obtained. Okay. So V steam table minus volume of ideal gas divided by volume of steam table. So because that is our actual volume, and if I do this multiplied by 100, so it means nothing but if I try to find the percentage change of the volume when we are taking it from the steam table, which is our actual volume relative to that only, and if we compare it with the volume which is predicted from ideal gas equation, we have marked some numbers over here. So you can see these numbers are nothing but our percentage error obtained using this particular equation whatever I have mentioned. Okay. So you can see that at the value of very low pressure, say 0.8 kilopascals, and high temperatures, you can see every time our ideal gas equation is actually giving perfect relationship. So because of that we are getting exact value of the volume identical to that of volume given in steam table. Okay. Then for 10 kilopascal also almost the same thing is applicable. However, if I go to slightly high pressure of 100 kilopascal, the change of volume has now started happening. Okay. So you can see that with the slightly high pressure or with the intermediate value of pressure, we are having some error in our measurement, and as our temperature is increasing, because ideal gas equation becomes more prominent at high temperature, so this assumption is correct. So because of that the error has actually decreased upon subsequent increase of temperature, and finally it has become almost zero. Okay. Similarly, if you see for 1 megapascal, for 1 megapascal now we are having actually significant amount of error encountered. Okay. So what we have done, this dashed line is placed over here. So this dashed line is nothing but it represents the demarcation of the regions in superheated zone where ideal gas equation is applicable for accuracy less than better than means error less than 1%, and in this particular zone so this error is actually less than 1%, and in this particular zone which is on the left of this dashed line we have value of error greater than 1%. Okay. So everywhere you can see that where we are having high pressure and low temperature, in that particular zone the assumption of assumption of ideal gas is not applicable, and our error encountered because of the ideal gas equation is actually greater than 1%. Okay. Now apart from this let us now try to see some more equations of state. So already I have told you that almost all the gases at the condition of low pressure and high temperature behaves as ideal gas, for which the equation PV equal to RT is applicable. Okay. However, what will be happening if I go to a situation of pressure and temperature other than these specific conditions? In that case, we will having actually variation in our behavior of the gas, and these particular gases many times we call as real gases, and their behavior cannot be expressed by this particular equation of state PV equal to RT. So for such equations we say that PV is equal to ZRT, okay, where this particular value of Z is something which is referred to as compressibility factor. Okay, so this particular compressibility factor will be coming into picture when we are having actually the molecular interactions of importance, and volume of molecules is actually volume of molecules is considered into is taken into consideration, okay, and it is not negligible relative to the size of the container or size of the system which is holding a particular gaseous substance. Okay, so now the value of this compressibility factor, it is nothing but it represents the deviation in the behavior of a gas from the ideal nature. Okay, so particularly for ideal gas, if we are having ideal gas condition applicable, for ideal gas value of Z will be 1, and any behavior other than ideal, we may have the value of Z either less than 1 or it may be greater than 1. Okay, so now under some conditions this value is less than 1, under certain conditions this value is actually greater than 1. So that now let us try to see for some gaseous substance. So over here I have nothing but compressibility factor. I am representing this compressibility of nitrogen over here. So this curve is particularly for nitrogen, and we have wide range of pressure and temperature over here. So you can see pressure is actually varying from 0 to somewhere close to 40 megapascals, and compressibility factor, because I have already told you that PV is equal to ZRT. So because of that, the definition of this compressibility factor Z will be nothing but PV by RT. So that is what PV by RT I have plotted along the ordinate. Okay. So now in this curve you can see this is the liquid vapor dome of nitrogen. So this is our saturated liquid line. This is critical point for nitrogen, and this is saturated vapor line. Okay. So now for the nitrogen, you can see I have over here given the multiple temperature lines. So this particular temperature line is say for 110 Kelvin, 130. So like that, the temperature lines are for different values of temperature. Okay. So one important thing you can see over here, that when our value of pressure is very small, so when our value of pressure is decreasing, corresponding to that the value of Z is actually approaching towards 1. Okay, so for low pressure value of Z is actually approaching towards 1, and at the same point of time when our temperature is close to ambient temperature, okay, so 300 Kelvin is nothing but 27 degrees Celsius, and 27 degrees Celsius is normally our ambient temperature which we consider. So when the temperature is close to ambient temperature of 300 Kelvin, corresponding to that, at least up to the pressure of 10 megapascals, when nitrogen is behaving as ideal gas. So even up to very high pressure of 10 megapascal, our gas is actually nitrogen gas behaves as nothing but ideal gas, because value of compressibility factor Z equal to 1. And beyond that, at the same temperature, if we go for beyond high pressures, then our value of Z is actually becoming large. Okay. One important point you can identify over here, that close to the critical point. So close to the critical point, we are having value of Z as less than 1. Okay. So close to critical point, you can see our pressure is maximum going up to 10 megapascals. So when we are close to the critical point, during that time what will be happening, we will be having nothing but moderate. So in this particular zone we will be having moderate value of density. So because of the moderate value of density, what will be happening in this particular zone, now our temperatures are though different. These are varying over the wide range, but the value of density is moderate. So because of that, molecules will be at sufficient distance from each other so that they can experience the attraction forces. Okay, so if molecules are experiencing the attraction forces, because of the attraction forces, now they will be actually occupying less volume. So if they are occupying the less volume than the ideal behavior, because in case of ideal gas, there should not be any molecular interactions. Okay, but over here what is happening, close to this critical point, okay, we are having actually moderate density. So because of that moderate density, what will be happening, molecules are having distances such that their attraction forces will be becoming prominent. If their attraction forces are becoming prominent, obviously they will be occupying lesser volume. So over here what will be happening, they will occupy less volume in comparison to the volume that of ideal gas behavior. So if they are occupying less volume, so value of this Z factor will be less. So in this case, value of Z factor, that's why it is less. When we are going to this very high pressure zone, so you can see clearly at high pressure zone, irrespective of the temperature value, value of Z is actually greater than 1. Okay, so what will be happening in this high pressure zone? Here in this high pressure zone, we will be having very high density. So if we are having very high density, it means molecules will be very closely packed. So if molecules are closely packed, in that case we will be having nothing but repulsive forces between the molecules. Okay, so because of the repulsive forces, what will be happening, molecules will be now having some, or molecules will try to occupy wider volume in comparison to that of the ideal behavior, whatever they were actually supposed to have without any interactions. Okay, so because of that, in this particular region, we are having value of Z as nothing but greater than 1. Okay, so this particular diagram is actually applicable for nitrogen. Now, if we try to see, or if we try to go into more details, we will be finding that for each and every gas, we are having almost same type of diagram. Okay, so it means that it becomes very difficult now, that if we have to refer to any particular gas, every time we have to refer to its compressibility diagram. Okay, so what we do, we are having one generalized diagram. That particular generalized diagram is referred to as Lee-Kessler diagram for simple fluid compressibility factor. Okay, so for simply compressible substance, we are having one standard Lee-Kessler diagram, and this particular Lee-Kessler diagram, what it does, it plots all the behavior for all the different substances in terms of reduced pressure and reduced temperature. So we write over here P reduced. So P reduced is nothing but our actual value of pressure divided by critical pressure. Okay, similarly T reduced is nothing but value of temperature divided by T critical. So if I just go to the previous slide, so what you are having, corresponding to this particular point, you can see for nitrogen, this is our critical pressure. Okay, so this is PCR for nitrogen, and the temperature line which is passing through this one, so it will be close in between 110 and 130. That particular temperature line will be giving us nothing but T critical. Okay, so now if I divide the whole diagram, whatever the value of pressures I am having and whatever the value of temperature I am having, if I divide each value of pressure by its critical pressure, so corresponding to the critical point, I will be having value of PR, which I have defined as nothing but P by PCR. So at critical point, its magnitude will be 1. Similarly, magnitude of TR will be 1 at critical point. Okay, so if I do this one for the different compressibility diagram. Obviously, the location of critical point will be same for each and every substance. Okay, so that's why this reduced property is nothing but it's a way of representing all the values of properties on a common diagram. Okay, so that's why you can see over here in this diagram, I have actually given the value over here as reduced pressure, which is equal to P by PCR. And similarly for temperature also we are writing TR, which is nothing but T divided by TCR. Okay, so clearly you can see when we are having this critical point. Okay, so at the critical point value of P R is 1. Similarly, if you try to follow the temperature line which is passing through the critical point, the value of if you once again go through the temperature line, you will be finding that value of this particular reduced temperature is also 1 at this point. Okay, and so it means all of you please keep your microphones muted. Okay, so what we will be having, at critical point uh, PR, P reduced and T reduced as nothing but equal to 1. Okay, so it means in this common diagram, now irrespective of the type of gas, if you have to find out compressibility factor, you can refer to this diagram. And one more thing I can conclude from this diagram, that whatever the things I described, particularly for the case of nitrogen, that almost the same things are applicable for generic nature of the curve also, where you can see that for low pressures value of Z is approaching to 1. There is some temperature condition corresponding to that. Our compressibility factor is equal to 1 till very high pressures also. Okay, and near to the critical point we are having a zone of Z less than 1, and at very high pressures irrespective of the value of temperature we are having value of Z greater than 1. Okay, this is now the Lee-Kessler diagram. Now this diagram is also actually experimentally also verified for different gases, because I am telling you that this particular diagram is applicable for each and every gas. Okay, so for different type of gases, this diagram is actually experimentally verified, and you can see the comparison of Z factor for various gases. So these lines, whatever are represented, these lines are nothing but from the generalized nature of the diagram, PR and TR, and whatever these points we are having for different gases, these points are nothing but the experimental observation. Okay, so we are having these lines as average curve based on the data of hydrocarbons, and all these points we are getting for different gases actually, the experimental point. Okay, so it means while we are presenting the data in reduced temperature and reduced pressure form, it shows a good generic behavior. Okay, uh, now let me go once again to notepad. So what I have told, that one of the way to show the real behavior of the gas is nothing but include our compressibility factor Z into our ideal gas equation. So ideal gas equation was PV equal to RT. So if I write PV equal to ZRT, then obviously this Z will be able to specify the behavior of particular gas. Okay. Now apart from that, we may also have certain we are having actually different equations of state which actually specifies the behavior of a real gas. Okay, so one such equation of state is referred to as cubic equation of state, and as per this cubic equation of state, what we are having, P equal to RT divided by V minus V minus A divided by V square plus CBV plus D into B square. Okay. So this is also one equation of state which is referred to as cubic equation of state, and this cubic equation of state actually gives the behavior of a real gas. Okay, so for this particular equation you can see over here that A, B, C and D are nothing but some coefficients. Okay, and if the value of all these coefficients, if you say A equal to B equal to C equal to D equal to 0, so if all these coefficients are 0, then our behavior will be becoming exactly identical to that of nothing but our ideal gas equation. Okay, so this is one point. Apart from that, we have one more very popular equation. So that equation is particularly referred to as van der Waals equation of state. Okay, so if like these equations are nothing but, if you are not referring to the compressibility chart, by just using these equations also you can specify the behavior of the gas. Okay, so as per the van der Waals equation of state, we are having P plus AY V square into V minus B will be equal to RT. Okay, so in this particular equation we refer that this our first term, whatever I am writing A by V square, it is nothing but representative for molecular interactions. Okay, so this term actually accounts for molecular interactions, and the term B, whatever we have included over here, it is nothing but it accounts for the molecular volumes. So if we are like taking care of the very two basic assumptions in our ideal gas equation, then obviously we will be able to relate our real behavior of the gas. Now if I just plot the PV diagram, so on this PV diagram, say this is my liquid vapor dome. So corresponding to the PV diagram, it is observed that we are having almost horizontal line close to the critical point. So if I represent this as nothing but my constant temperature line, and obviously this constant temperature line is passing through critical temperature, so that's why this temperature will be equal to nothing but TCR. Okay, so if we are having a horizontal line over here for which temperature is equal to TCR, and so corresponding to this critical point, I can clearly write that the slope del P by del P at T equal to T critical will be 0. Similarly, del square P by del V square at T equal to T critical will also be equal to 0, because the nature of this line, temperature line, is almost horizontal close to the critical point. So because of that, its first and second derivative on a PV plot at critical point will be equal to 0. Okay, so if you now do these derivatives, and if you want to obtain the value of A and B, finally you can find the value of A as nothing but equal to 27 into R square T critical square divided by 64 into P critical. Okay, and similarly if you obtain the value of B, you will be finding R into T critical divided by 8 times of P critical. Okay, so these, once the values of constants A and B are known, you can actually substitute value of these coefficients in your equation of state, and you can relate the pressure, volume and temperature, okay, for a substance, where you are actually accounting for the molecular interactions as well as the molecular volumes. Okay, so apart from this equation of state, there are many other equations of states are also available, but because I have already given you the generic nature of the compressibility chart, so by just using that we can do majority of our problems, particularly in the course of thermodynamics. So that's why we will not go beyond this point. So this van der Waals equation also I have just introduced for your knowledge only. Okay, so what I'll be doing now, I'll stop at this point, and let me take up the next topic. So from our next lecture, we will be starting with the next module, so that I'll now start in next lecture only.